back. Sort of. I'm going to do my best to get on some kind of like regular schedule. Like, as you can see, I'm on like a flexi thing now. So for at least a couple hours during the day, I can do that and into therapy and whatnot. Oh, but first, a cover my butt disclaimer. Now, we are going to be working with flammable liquids that make flammable mists, as well as heat sources like toaster ovens and things like that. This isn't any more dangerous than anything you deal with on a daily basis with your 3D printer, but that's not to say that that can't be dangerous, so you consider yourself disclaimed and warned. All right. For those of you who are just wandering in and want to get to the good stuff and want to skip 60 seconds of me talking, look in the navigation links in the video description, skip ahead to like intro to experiment or background info or whatever. But for the rest of you who have been wondering where I've been this whole time, hi, how you doing? How's your month been? I plan to come back with a video like, what have I been doing this month, and talk about all the crazy stuff that's happening around, because for those of you who don't know, I live in Center City, Philadelphia, so look up Philadelphia and riots, and, you know, you can see what's been going on. I had to get out of town for a couple days and come back, but I'm going to try to get back to normal. Now, during this whole time, I've been doing crazy stuff. For example, just in this screenshot here, we have hot end cooling experiments, part cooling experiments, Coanda effect cooler, no sensor mesh leveling, alternative print surfaces, unusual heater blocks, modified nozzles, DIY mix-free ambient silicon molding, groove mount hot end belt tensioners, PW1 TAM noise filtering, motherboard, SMD component modification, active belt tension monitoring, carbon fiber Y sled, heated bed insulation, firmware modding, etc., etc., etc. So, this is one of the crazy things that I was doing, which is getting PLA prints drunk. So this I had in my brain for a while, and I tried it and it worked. Spoiler alert. But there's part of me, I had to rerun the tests in like 6 different ways, because there's part of me that's like, surely somebody would have said something. Somebody would have said something by now if this were a thing. But apparently it is a thing. And I can prove it. Also, all of this is totally easily tested by any of you at home. I mean, you'll see once we get into it. Along those lines, I don't know to what extent it's a thing, and I only dealt with thermal testing for reasons that will become clear as I yap further. And there will be a summary at the end where we go through all of the results of the experiments and talk about, you know, areas of future work, things like that, shortcomings of the experiments, etc., etc. I think somebody like Stefan from CNC Kitchen, if you don't subscribe to Stefan's channel, go ahead and do it, because he tackles some really interesting subjects in very interesting ways. But he has a self-made like mechanical property setup that he uses for 3D prints, and I've been dying to make a copy of that for myself. I just don't have the room to set it up, so someday. But until then, this is something I could kick to somebody like him to maybe test out further. Or to just run it once and be like, Alex, you're crazy, this isn't a thing. Background. If you recall, I was working on a bunch of like 3D printed shrouds and like cooling fan stuff, and that all got held up because of the whole shipping and COVID thing. I was trying to get a thermal camera rigged up, and like I can't get any of the elements over here, and they were all being used for, you know, testing and stuff like that. I did continue with a whole bunch of that, like hot end cooling and parts, you know, like printed parts cooling and things like that. But as you know, with some of those designs, you have, you know, surrounds and nozzles and funnels and all kinds of things that sit very close to the business part of the hot end, which is, you know, 200 degrees or so, give or take. As a result, a lot of people print in more materials that have higher temperature deflection than PLA, which is the stuff that's easy to print and cheap and ready available and biodegradable and like all those lovely things. I 99% print in PLA. I only bust out the other stuff if I absolutely need it for a particular reason. So all of my cooling funnels and shrouds, like almost all of them, have been printed out of PLA. I've shown a couple different ways that I anneal stuff. Usually I will take like hot water, boil water, wait for it to cool a little bit, toss the part in, and then that has some problems. First of all, like all the water and the boiling and all that type of stuff. But secondly, you know, the parts still can deform, and if it's hollow, it, you know, it floats on the top and it's a pain in the butt. And you can also cook parts on your 3D printer bed, which I do as well, which works out fine if they're printed solid and fairly flat and don't have details that'll get all mangled. So what we are doing here is solvent-induced crystallization, or solvent annealing, I guess you could call it. And the purpose of this particular test was to improve the heat deflection properties of polylactic acid printed parts. Because as you know, PLA starts to soften around like 60-65 degrees or so. The glass turns the blah blah words transition temperature, and that's just not enough for a lot of things. So we're going to be annealing with a solvent, specifically a mixture of less than or equal to 50% distilled water and greater than or equal to 50% ethanol or ethyl alcohol. And to that purpose, I bought a $20 bottle of hooch. Why, Alex, I hear you ask, did you go through the expense and the bother of getting Everclear when you could just go grab rubbing alcohol off the shelf of any drugstore? Well, I'm glad you asked that disembodied voice in my head. This is time for a little bit of chemistry, and chemistry is not one of my strong suits, so a very little bit of chemistry. So Everclear is just a brand name for a rectified neutral spirit meant for human consumption. So as a result, it costs a little bit more because it falls prey to all the vice taxes and whatnot. But it's very high purity, pretty much as close as we can get to just alcohol and water. Ethyl rubbing alcohol, on the other hand, is not a pure reagent. It's meant for the purpose of, well, rubbing and disinfecting and things like that. So it's 70%-ish ethyl alcohol and then 30% like mystery meat. And let me explain what I mean by that. Ethyl rubbing alcohol, by law here in the US of A, has to conform at least to what's called Formula 23-H, which means it has to have at least 5% acetone, at least 5% methyl isobutyl ketone, and then the rest can be a mixture of water and other things like denatonium benzoate, which is where we get the term denatured from, denatonium. It can also have other, in quotes, denaturants in it, as well as colorant, perfumes, and oils, because if it is rubbing alcohol for putting on your skin, alcohol tends to dry it out, so sometimes they'll put oil in there to keep you from using too much moisture. So, in other words, it's not lab-grade stuff. Now, let's talk about what is lab-grade stuff, or reagent-grade stuff, or food and lab and reagent-grade stuff, whatever. There's a bunch of different options, and that's my point here, is you're still not getting pure stuff. Now, it may be completely irrelevant, or perhaps not, but I don't want to go through the bother and the expense if it doesn't really matter or it's going to be worse. For example, in my searches, some lab-grade stuff had isopropanol in it, methanol, benzene, ethyl acetate, MEK, pixie dust, eye of newt. It really seemed to vary from one manufacturer to another. For most of the stuff, you could actually find out what was in there, but for others, I guess it was up to the imagination. Also, for the really high purity stuff, there was almost always the warning, contains trace amounts of toxic benzene. And the reason for that is that you can only get ethanol about 95-ish% pure before you have to chemically remove the rest of the water to get it to 100% pure. And typically they do that through azeotropic distillation, which means they put chemicals in there like benzene, for example, to draw out the rest of that water. Then they remove as much of that benzene as they can. Benzene, consequently, was one of the 3 ingredients in Dip from Who Framed Roger Rabbit that the judge used to execute cartoons, the other 2 being turpentine and acetone, so a little trivia fact for you there. And I just, as a general rule of thumb, try to avoid as much of this stuff as I possibly can if it's potentially dangerous, particularly if I'm going to come in contact with it on a daily basis, possibly absorb it through skin or breathe in the vapors, that type of thing. I do personally know people who have died of leukemia from repeated daily exposure to denatured alcohol, so I'm a little skeezed out by the whole thing. Also, I live in the nanny state of Pennsylvania, and I don't want to have to mess around with industrial alcohol user permits. Yeah, that's an actual thing. I'm sure it's not a whole lot of red tape, but screw it when I can just go down and get a bottle of Everclear on the corner. Now, if you can't get Everclear or, high purity moonshine or high purity vodka where you are, I will put a link to Amazon store here where you can get lab grade denatured alcohol that has all of the ingredients listed. Should be okay. It's less ethyl alcohol than Everclear, ironically, but there's also water, but then isopropyl alcohol and methanol. Methanol's not fantastic, but better the devil you know than the carcinogen you don't. Now, the 190 proof stuff is not necessary, as you will see in the test, but we do need at least like 50%-ish, so 100 proof and above is fine. Just remember, as the proof goes up, the alcohol content goes up and it becomes more volatile and flammable. Onto the testing apparatus now. Basically, the only thing we're going to need here is our 3D printer heat bed, some plastic bags, a couple vats, and a convection oven where we're going to be testing the melting points of these. That's the best way I could get uniform heat distribution, and it's pretty good, within a couple degrees reasonably near the center of the oven. So I ran through about half a dozen different types of tests here, and let me cover them for you real quick. The first one was to print out these 100mm bars from natural clear virgin PLA, and I used a 50% gyroid infill on those. Second was to use slightly thicker, taller bars with 3 walls and 20% gyroid infill. Oh, and the reason I use gyroid infill is because, if you don't know, it's an open infill pattern, so anything you pour into there can get throughout the entire print. So if you have something like a drain hole, you can pour in your alcohol and then dump it out when you're finished. The third print is vase mode, or whatever, single wall mode, with these ringing blocks that I repurposed from another project. The fourth test were these cone support type of deals to simulate like a nozzle being close to a print head. The fifth and sixth tests were these cubes with an open face printed with 2 perimeters. And then I did a little bit of a bonus test, which was intended to be another full test, but you'll see why I just call it a bonus. Other testing parameters. When I say boil or hot water, it's just, well, boiling a pot of water like this, either dumping it right in when it's boiling or waiting for it to cool down and then leaving the part in until the water cools enough to withdraw it. If it says bed, then I heated it under this enclosure for 1 hour on a heat bed. The alcohol tests were done with Everclear in different concentrations at different heats and for different durations. And then the rubbing alcohol was done with, well, just this rubbing alcohol in the same way as the ethanol, but I just used the off-the-shelf stuff. I had 2 different ways that I tried to safely heat up the ethanol without causing, intoxicating vapors. One was under a heat lamp, and the other was just to put it in this metal container. I think it's like a bread pan or something like that, and then heat it up on the 3D printer bed to 45 degrees or whatever target I was going for. And of course, this room has extra ventilation, carbon filtering, an extra smoke alarm, and several fire extinguishers. So quick preface here, these are all relative tests, so rather than doing absolute values like when they melt and how much they deflected, I used a control sample for each of them, so there will be a untreated PLA object in all of these tests that you can use as a relative guide for the efficacy of the particular treatment. Also, I do have thermometers in some of these shots, but they're just there to show the relative heating up and cooling down or whatever. They don't show the actual temperature because A, they're not accurate, and B, they lag behind the temperature that's actually going on in the convection oven. And third, I'm going to blow through all these tests, just show you fast forward pictures of the melting process and talk over it. Then we will discuss the results at the end just to save time and keep everything nice and tidy. So the first test was the 100mm bars with the 50% gyroid infill. They were all treated with either the Everclear or rubbing alcohol at ambient temperature for an hour. They were boiled or put on an 85-degree bed for an hour, and then there was the control all the way to the left there. Now you can see immediately the control starts to melt as I heat it up, followed by the rubbing alcohol, which seems to have a little bit better deflection, but not as much. Then that's followed by the Everclear that was soaked for an hour at room temperature. And then finally, as I fast forward more and turn the heat up, the control is practically liquid, but we get a little bit of movement here on the boiled piece and the piece that was annealed on the bed. Test number 2 was the same deal, but with thicker bars and the sparser infill, so these are much larger bars. And as you can see here, I marked with Sharpie on all of them. We had the boiled, the 85-degree bed. I also added alcohol ambient overnight in a bag. Then we have the control that I added an extra L on the end for luck, I guess. Then 1 hour in the ethanol at 45 degrees Celsius and 1 hour in the ethanol at ambient temperature around 25, 27. And we get pretty much the same result. The control starts melting immediately, and then basically all of the other treatments were effective to 1 degree or another. As far as heat deflection goes, cooking it on the bed seems pretty good in this situation, but these are pretty much the ideal conditions for doing that. A very flat, evenly dimensioned object without a whole lot of details, that's going to do very well cooking on the bed. And you can see the alcohol at ambient has a little bit more movement, and the control up on the top was pretty much, rainbow shaped at this point in time. For the next test, I decided to do the shell-only ringing test that I recycled from a previous experiment, and I did 2 variations. One weighted down with bolts so that I could see the structural integrity, and the other just to watch the droop as I turned up the temperature. So again, you can see right here, the control on the left almost immediately falls over, followed by the ethanol annealed on the right, which has a much more structural integrity at higher temperature than the untreated does. And then in the middle, we have the boiled piece, which you can see is already a little deformed from the boiling, but deflects heat very, very well. Right here, you have the control on the left, and to the right of it, in the middle, that's the alcohol treated piece. This next test I kind of did just for kicks, so I don't have decent video of it because I was holding the camera and it's too shaky to play in fast forward. But I use rubbing alcohol versus ethanol versus two controls. So the controls are on the corners on the left and the right, and as you can see right here, they definitely drooped before the other two did. And just to show you the aftermath of the deformation, those two smileys on the top there, these are the control samples. As you can see, they both drooped pretty easily. And then both the Everclear and the rubbing alcohol, they held their shape pretty good. I don't, unfortunately, remember what temperature I did these to, but definitely as a comparison to the control, much better temperature deflection. Next up, we have the cones, which I printed out to kind of simulate, a heating funnel that would be sitting near the hot end or something like that. For this, I just did the control versus taking the ethanol at 50% concentration and cooking it on the 3D printer build plate at 45 degrees for 1 hour. Now, this test was much less interesting to look at, but this was more about distorting the shape or preserving the shape than it was about like catastrophic failure or anything like that. So after I heated these up, I can sit them side by side and see the difference between the control on the left and the alcohol treated on the right, the Everclear treated. Very obviously, there's a lot of distortion on the nozzle. You can see on the control, there's a whole bunch of curling on the bottom where there is none on the alcohol treated part. And then if we take a set of cheap calipers and check the dimensions for the alcohol treated part for this 40 millimeter print, we're pretty much still spot on where we were. Also, if you take that and check the concentricity, the rounditude of the part, you can see that it pretty much maintained its circular shape, whereas if we look at the control, it's quite obviously gone south, and now it's more of a diamond than a circle. On to test 5 and 6. This was about time and temperature that these objects spent in the alcohol. See, we're kind of whittling down our options down and seeing what's effective and what's not. So this shape, as a refresher, is a cube that's open on one side and printed with 2 walls in natural PLA. In this case, we used a 50-50 alcohol to distilled water ratio, so about 100 proof, and we have 2 batches of 2 variations. So for the first, we had 45 degree alcohol that was soaked for 7.5 minutes versus 30 minutes. Then we had ambient temperature around 25°C for 7.5 minutes and then 30 minutes, as well as a control sample that we can compare against. And those were, again, placed in the convection oven. At first, I set this to around 120 degrees, which is about 125 degrees in this oven. And as you can see right here, the center is the control sample. That goes first, followed by the 25 degree, both 7.5 minute and 30 minute samples. But after it sat there for like a minute or two and nothing moved, I decided to crank it up past 125 until I could start to see some catastrophic failures. And if you look closely, as the heat is rising here, the 25°C ones are not lasting nearly as well as the 45°C. And as we start to get catastrophic failures, those are the first ones to go, followed by the 45 for 7.5 minutes and the 45 degree for 30 minutes. Don't worry about taking notes. I'm going to sum all this up in the end for you. So having seen that using a little bit of heat was better than room temperature, I decided to see if moving up to 75% alcohol was better than 50% alcohol, and then use a control sample to compare against. So as you can see right here, as with all the other tests, the control sample goes pretty quickly. Now, I set this originally to heat to 150 degrees or so, and that just wasn't doing it for the other one, so I had to just crank it up as high as it would go and then wait for them to melt. So if you look right here, they both generally start going at the same time, but it looks like the 75% starts to go first, and then that's confirmed when the 75% actually fails catastrophically before the 50%. And as promised, here's our bonus test. Now, the only reason it's a bonus test is because it didn't work out quite how I'd liked, and I didn't really have the gear to do it properly. But if one of you has one of these Polymaker Polysure things lying around, you could try this at home by just substituting the isopropyl alcohol that goes in it for Everclear or, whatever 100+ proof grain alcohol without additives you could find. Now, these devices are a little bit expensive for a simple boy like me who doesn't do any print smoothing really, but if Polymaker wants to send me one for experiments, I won't turn my nose up at it. Consequently, I'll put a link to these in the video description, not saying you should buy one, but if you're interested and you're going to buy it anyway, I might as well get a couple bucks from it. What I did have was this craptacular diffusamajon thing that I got from the trash out front of the thrift store a long time ago. This is one of those ultrasonic, essential oil diffusing misters. So I'm just going to fill it with 50% ethanol and see what happens. Now, since this mist will be both flammable and intoxicating, I put this little bottle on top just to make sure that it would condense on the outside and run down as opposed to being thrown up into the air. See what I mean? But here's the exciting part. Wait for it. Wait for it. Oh yeah, bathtub rave. Now, the problem I had with this thing is that it sucks. And it didn't mist as much as it did just kind of throw alcohol around the bathtub. So as you can see right here, there's just not a whole lot going on there. So unfortunately, I did get it to eventually fog, but I had to add quite a bit of water to it. It just didn't have the girt I need to do it. So I'm probably going to buy a couple of these ultrasonic misters that are more powerful, and then a sealed Tupperware container to keep the vapors from doing anything bad, and then maybe an external heat lamp to bring it up a little bit above ambient, get it to 40 degrees or so. But eventually I did get it to fog up, so I let it run for an hour-ish at, I'm guessing 30-40% or so water or alcohol to water, and then tested the that part against the control in the convection oven. The A is alcohol, obviously, and the C is the control. Now, as you can see, the control still goes first, but the alcohol is starting to deflect much more than it did before. So I don't want to say necessarily that the mist thing doesn't work as well, but maybe for the concentration of alcohol that I used, it doesn't work very well. And here's a little peek at them next to each other, control on the left and alcohol on the right. So, on to, kind of the point of this, dimensional stability along with the temperature deflection. If we measure the control that was printed on the slicer at 100 millimeters, you can see it's right around 100 millimeters, 0.04 off. Now, if we switch from that and we take a look at the boiled part, well, that's a lot smaller. We lost several millimeters there, a couple percent shrinkage. But if we look at the Everclear treated rod, it's almost exactly where it was with the other, within margin of error. Same thing goes for the width. If we look at our control sample of this supposedly 10 millimeter wide, it's a little bit over 10 millimeters. If you look at the boiled part, that's quite significantly shrunk down to about 9.8 something. And then the Everclear part is pretty darn close to the original 10 millimeters. Also, looking at difference between the alcohol and cooking it on the bed, kneeling on the bed, the alcohol part, of course, as we've already established, pretty much maintained its dimensions, whereas the bed became a little bit more distorted and it also got extreme elephant foot. So conclusions, well, it's quite obvious from all of these tests that it does work. So going back to my original statements 25 minutes ago, it is, quote, a thing. Also, as far as the ethyl rubbing alcohol question, that did have an effect as well, although not as pronounced. And I did have a little bit of a problem because of the, quote unquote mystery meat that's in there. Some of the alcohol treated samples, particularly the ones that sat overnight, delaminated easier than the other prints did. But some of the boiled samples delaminated as well if I cook them too hot, and you can see the extreme shrinkage here. So it's quite possible that some of these prints just were under extruding a little bit, which is why I printed tons of them. So further work, further testing, whatever. It's quite obvious that this was just something that I had done for myself. I did, when I saw that it was going to be successful, kind of gussy up the tests a little bit for you all, but under better controlled equipment with better gear, that would be great. Nailing down the length of time that's optimal is also something that has to be done, as well as the optimal temperature. Much more testing has to be done with the proper vapor stuff. It would be great if ambient or just heated by a lamp, vapor treatment worked for these prints in PLA. That would kind of just change everything. As well as the concentration of alcohol to distilled water. The mechanical properties have to be investigated. I'm not set up to do that, but I know some people are. As well as testing with infill patterns, drilling holes, letting the alcohol inside to anneal the infill and that type of thing. Also comparing it to other filaments like raw PLA to chemically treated PLA to PETG to ABS, etc., etc. So anecdotal observations from me from this small uncontrolled data set here. The higher temperature does help, as in like heating up the alcohol to like 40, 45 degrees, not up to dangerous combustion temperatures or anything like that. But ambient does work, just not as well. Also, leaving it in longer doesn't necessarily make it better. You saw as the 7.5 versus the 30 minutes in the alcohol, there wasn't really that much of a difference. That tells me that the crystallization happens very quickly. So probably within the first 5-10 minutes, it's about the best you're going to get. In terms of concentration of alcohol to water, it doesn't necessarily seem that a higher concentration is better. In fact, we saw in that test where we did 75 versus 50 that 50 was better than 75, which means something around 50% alcohol, 50% water, i.e. 100 proof or 120 proof, is probably the sweet zone, but that may or may not change depending on temperature and length of time you leave it in there and things like that. We also saw that the misting works-ish, although a lot of experimentation has to be done there, and the ethyl rubbing alcohol off a shelf, if you just want to try this, works in quotes, but because of the mystery meat, I don't know what's in your rubbing alcohol, so it may be a disaster. And in terms of comparing it to heat anodization, it definitely has less heat deflection, but it's much, much, much better than raw PLA. But it does have much better dimensional stability, which is very important because who cares if your parts hold up to the heat if they're all distorted, and it's a lot faster. I mean, if we're talking 5, 7, 10 minutes versus cooking something for half hour, 45 minutes, an hour on a build plate or something like that. And like I said at the beginning of the video, test me. Go ahead and test this. It seems too simple to be true, particularly when there's been all this hassle about annealing things with heat and parts melting and that sort of thing. So give it a go. Thanks for sticking around through all that. Hope you learned something and it was fun. If you like this type of content and you want to support the channel, go ahead and check out my support links in the video description below. Usually I say if you have any questions, leave them in the comments and I'll try to get to them. Things are weird these days and I don't want to overpromise by promising anything at all because Murphy's Law has just been coming down on my head pretty hard. But I'll see what I can do. And again, if any of this is real easy to test at home, so if any of you want to pick this up and run with it, see what happens, let me know what your results are. And until the next video, get out there and make something awesome.